Hello everyone, I'm Annemarie Rickmann and I will present our work on self-training with uncertainty dependent label refinement across domains. In our work, we focus on the task of white matter hyperintensity segmentation. White matter hyperintensities can be observed as hyperintense regions in the white matter in MRI FLAIR scans. They are common in elderly people, but can also be an indicator for risk of dementia and cognitive decline. Although convolutional neural networks have already achieved remarkable performance for white matter hyperintensity segmentation, there are still some challenges, like the variability and scattered spatial distribution of the lesions, as you can see in the images on the bottom, or the class imbalance, especially for patients with low lesion loads. The biggest challenge, however, is, as in a lot of medical imaging segmentation tasks, the limitation of expert segmentation. The available data usually cannot cover the wide range of MRI acquisition protocols, scanner types, or patient statistics, which leads to the problem of domain shift when applying the trained models to unseen data. In our work, we use the dataset from the white matter hyperintensity segmentation challenge as our labeled source data. But our goal is to apply the model to the ADNI2 database, which contains a large amount of scans from different sites and scanner types. We used an unsupervised domain adaptation approach to deal with the domain shift between our source and target data. Self-training is an iterative approach for unsupervised domain adaptation, where a segmentation model is first trained on annotated source data and then applied on a random subset of the target data to infer so-called pseudo-labels. These self-generated pseudo-labels are then used to fine-tune the model. The pseudo-labels then get updated by the fine-tuned model. In a last step, the pseudo-labels are used together with the source data to retrain the model from scratch. However, due to the domain shift, pseudo-labels tend to be noisy, especially the initial pseudo-labels. Therefore, in our work, we propose an approach to estimate the reliability of pseudo-labels to avoid propagating label errors. We call our method STRUDEL, self-training with uncertainty dependent label refinement across domains. The first difference to the standard self-training approach is the use of the label prediction algorithm, short LPA, which is an existing software for white matter hyperintensity segmentation that was shown to achieve robust results across domains. We use it in the pseudo-label initialization step to increase the quality of initial pseudo-labels. Even though the quality of pseudo-labels has been improved with LPA, they are still quite noisy. Therefore, we propose an uncertainty-guided training process in the last step of the iteration. We estimate uncertainty maps of the network's predictions and use them in an uncertainty-guided loss function to reduce the impact of regions with high uncertainty. To obtain these uncertainty maps, we train the network with dropout layers and obtain Monte Carlo samples by running multiple forward passes at test time. The variance of these samples gives us the pixel-wise uncertainty map U. As you can see in the figure on the bottom, high uncertainty regions correlate well with errors in the prediction. We integrate the uncertainty into network training by using the uncertainty-aware binary cross-entropy loss defined in the second formula. This way, areas with high uncertainty, meaning the pseudo-labels might be wrong here, will have less impact. In our experiments, we use two different CNN architectures. First of all, the well-known UNet and an adapted UNet, which includes octave convolutions and squeeze and excitation blocks that we called OctSENet. We compare to the base model, which is the model trained on the source data and directly applied to the target data. This performs poorly, and in case of UNet is even outperformed by LPA, which has been shown to be more robust than some deep learning-based approaches. We also compare to two models that use labeled target data for training. The joint model uses a combined dataset of source and target data for training, and the fine-tuned model is first trained on source data and then fine-tuned on target data. Those two models, as expected, clearly outperform the base model and LPA. The self-training approach here is STRUDEL without uncertainty guidance. We can see that STRUDEL performs better than self-training for both networks, and in case of OctSENet even outperforms the joint model and fine-tuning model. In an additional experiment, where we removed LPA from the pseudo-label initialization step, we can see that the performance decreases by a large margin. This shows how important the pseudo-label initialization is. We have shown that self-training is a simple and effective approach for unsupervised domain adaptation in white matter hyperintensity segmentation, but it suffers from the problem of noisy pseudo-labels. The uncertainty guidance in STRUDEL can efficiently guide the learning process. We have also shown that using existing software like LPA boosts performance by improving the quality of initial pseudo-labels. Thank you for watching this video. If you have any questions, send me an email and check out our code on GitHub.